There is a place in the universe so empty that if you were somehow transported into its heart, you could spend millions of years traveling in any direction and never once encounter a single star. Not a dim star, not a distant star, not even a dead star, cold and dark and spent, nothing. The void around you would be so absolute, so complete, that the very concept of a night sky would become meaningless. There would be no night sky. There would only be night. Infinite, unbroken, total night. Interrupted by nothing except the faintest smear of light at distances so incomprehensible that the light reaching your eyes left its source before the earth existed. We are talking about the cosmic voids, the great holes in the architecture of the universe, regions of space so vast, so profoundly empty, that calling them empty feels like an insult to the word. We use the word empty to describe a room with no furniture, a bottle with no water, a field with no crops. But those things are crowded with atoms, saturated with air, buzzing with molecular activity. The voids are not empty in that sense. The voids are empty in a way that has no human analogy, no earthly equivalent, no adequate metaphor drawn from any experience you have ever had or could ever have on this planet. And yet here is the thing that should stop you in your tracks. Here is the fact that this entire journey is going to circle back to again and again, until its full meaning settles into you like something inevitable. The voids are not simply the absence of something, they are the presence of something we do not yet fully understand. Something is happening in those enormous hollows. Something shaped them. Something continues to act within them. And what is acting within them may be the single most important force in the history of the universe, a force so strange and so dominant that every galaxy you have ever seen in a photograph, every cluster of stars, every nebula, every cosmic structure that has ever inspired human wonder exists only because of what happened in the spaces between. By the time we are finished, you will understand why the emptiest places in the universe are not really empty at all. You will understand what they contain, what they reveal, and why they carry within them the answer to a question humanity has been asking for as long as we have had the capacity to look up and wonder. You will understand why the voids are not a footnote to the story of the cosmos. They are the story. But before we can understand what the voids are, we need to understand what they replaced. And that means going back. Not just back to the beginning of astronomy or the beginning of science. Back to the beginning of everything. Back to the moment roughly 13.8 billion years ago, when there were no voids, no galaxies, no stars, no structures of any kind. Back to a universe so different from the one we inhabit, that describing it requires us to abandon almost everything we think we know about space and time and matter and the way things distribute themselves across the cosmos. If you had been present at the moment the universe began, which is of course impossible for reasons that go far deeper than mere mortality, you would have seen nothing we would recognize today. There were no galaxies gathering in their local groups. There were no galaxy clusters anchoring their vast neighborhoods. There were certainly no supervoids, those cathedral-scale absences that we are going to spend a great deal of time inside before this journey is complete. In those first moments, the universe was not structured. It was smooth, extraordinarily, almost perfectly smooth. A hot, dense plasma of energy and fundamental particles distributed with a uniformity so precise that the variation from one region to another was measured not in percentages, but in 100,000ths of a percentage point. This is the first thing you need to hold in your mind as a kind of anchor, because everything that follows depends on it. The universe began almost perfectly uniform, and the universe you see today is magnificently, spectacularly non-uniform. Galaxies here, voids there, galaxy walls and filaments threading through space like a cosmic web, and vast, dark hollows where almost nothing lives at all. Something happened between then and now. Something turned that almost featureless beginning into the extraordinarily structured cosmos we inhabit. And the voids are the clearest, deepest, most dramatic signature of that transformation. They are the fingerprints of processes so fundamental that understanding them means understanding not just where galaxies are, but why anything is anywhere at all. We are going to follow those fingerprints all the way back and all the way forward to implications that extend beyond cosmology, beyond physics, into territory that touches the most ancient human questions about existence, meaning, and our place in an arrangement so vast that our entire visible universe may itself be a tiny corner of something incomparably larger. If you find value in this kind of journey, in the long, deep exploration of ideas that most channels never have the patience to pursue, all the way to their most profound conclusions, then staying with this channel matters. Not for any abstract reason, but because the people who support this work by watching, by sharing, by becoming part of this community, are the reason these explorations are possible. Every person who chooses to go deeper rather than stay shallow makes the next journey possible. And there is always a next journey now. Let us begin at the beginning. Not the beginning of the voids, the beginning of the universe itself, and the extraordinary, nearly invisible seeds from which both the grandest structures and the deepest absences eventually grew. 13.8 billion years ago, in the first fractions of the first second of cosmic time, the universe was smaller than a proton. This statement is one of those facts that tends to slide off the mind without really landing, so let us sit with it for a moment. The entire universe, not just the matter and energy we can observe today, but everything that exists, all of space itself, was compressed into a region smaller than the nucleus of a single hydrogen atom. The temperature at that moment was not merely hot, it was hot in a way that makes the core of our sun, burning at 15 million degrees, seem like a cool autumn afternoon. The universe in its first moments existed at temperatures so extreme that the very concept of individual particles had no meaning. Everything was energy, everything was everywhere, everything was the same. Then something changed. In the first billionth of a trillionth of a trillionth of a second, a process that physicists call inflation began. And what inflation did to the universe is one of the most dramatic and counterintuitive things that has ever happened to anything in the history of existence. The universe did not simply expand, it expanded at a rate so extraordinary that the mathematics required to describe it would seem like science fiction if we had not found the evidence for it written into the oldest light we can detect. During inflation, space itself grew by a factor of at least 10 to the power of 26. Write that number out. It is a 1 followed by 26 zeros. In a span of time so brief it defies human comprehension, the universe went from something smaller than a proton to something roughly the size of a grapefruit. That might not sound dramatic until you understand what that scaling factor actually means. If you took a single hydrogen atom and inflated it by the same factor that the universe inflated during those first moments, that atom would become larger than the observable universe is today. And here is where the seeds of the voids first appear, though you would never have recognized them for what they would become. During inflation, quantum mechanics was still operating, and quantum mechanics, at its deepest level, is a theory of fundamental uncertainty. Even at the smallest scales, even in conditions of perfect uniformity, quantum fluctuations exist. Tiny, random, unavoidable variations in the density of energy from one region to another. Before inflation, these fluctuations were microscopic, confined to scales far smaller than any atom. But inflation stretched them. It took those quantum whispers and amplified them to cosmic scales, imprinting them across the fabric of space like a pattern pressed into wet clay before it hardens. When inflation ended, the universe was left with a map. Not a perfect, smooth, featureless map, but a map with variations. Some regions were very slightly denser than average. Some regions were very slightly less dense than average. The differences were extraordinarily small, 1 part in 100,000, but they were there. And over the next 13.8 billion years, those tiny differences would be amplified by gravity into everything we see today. The slightly denser regions attracted more matter. They grew. They became the seeds of galaxy clusters and the great walls and filaments we observe today. And the slightly less dense regions, they gave up their matter. Gravity drained them, slowly and inexorably, pulling their sparse content toward the growing concentrations around them. Over billions of years, those underdense regions became emptier and emptier and emptier as the matter within them flowed outward along gravitational gradients toward the walls and filaments surrounding them. The voids were not carved out by some violent event. They were not emptied by an explosion or a collision. They were evacuated gently, steadily, over cosmic timescales by the same force that built every galaxy and every star. Gravity created the voids just as surely as it created the structures. The voids and the structures are two faces of the same process, inseparable, defined by each other, products of those quantum fluctuations from the first moments of time. This is the foundation, and it raises a question that should be forming in your mind already, even if you cannot quite articulate it yet. If the voids grew from the same seeds as the galaxy clusters, if they are simply the inverse of the structures, the emptied-out complement to the filled-in regions, then why are they so remarkable? Why do they deserve this kind of extended attention? The answer is that the voids are not simply the absence of structure. They are a precision instrument. They are a natural laboratory unlike anything humanity could ever build. And what they are measuring right now, silently, in the dark between the galaxies, is something so fundamental and so strange that its discovery 2 decades ago shook the foundations of physics in a way that has not fully settled even today. But we are not ready to go there yet. First, we need to understand the scale of what we are talking about, because nothing in this story lands properly unless you have a genuine, visceral, bone-deep appreciation for just how large these structures are. Numbers on a page are not enough. We need to find ways to make the size of a cosmic void feel real, even if that feeling is really just a controlled form of vertigo. Consider our own galaxy, the Milky Way. It spans roughly 100,000 light-years from edge to edge. Light, traveling at the fastest speed anything can travel in this universe, at nearly 300,000 kilometers every single second, takes 100,000 years to cross it. If you somehow shrank the Milky Way to the size of a standard dinner plate, roughly 30 centimeters across, then the distance between our solar system and the nearest large galaxy, Andromeda, would be about 8.5 meters. Not 8.5 kilometers, 8.5 meters. The 2 largest galaxies in our local neighborhood, separated by 2.5 million light-years, would be less than 10 meters apart on that scale. Now, hold that image, a dinner plate and another dinner plate, about 8.5 meters away. Got it? On that same scale, the nearest substantial void to our own cosmic neighborhood, a structure called the local void, would span roughly 300 meters, an entire city block. 300 meters of absolute star-free emptiness, scaled from a void that in reality contains almost nothing across a region of space tens of millions of light years across. And the local void is small, as voids go. It is a minor absence, a modest hollow, barely worth mentioning in the catalogue of the universe's great empty places. The largest voids we have identified are so much bigger that comparing them to the local void is like comparing a puddle to an ocean. The Boötes Void, discovered in 1981, spans roughly 330 million light-years. On our dinner plate scale, it would extend for nearly a kilometre. 1 kilometre of absolute emptiness, scaled from a void that contains, as far as we can determine after decades of searching, approximately 60 galaxies where our models predict there should be thousands. Some surveys have pushed that number slightly higher, but the consensus holds. The Boötes Void is so empty that it represents one of the most dramatic deviations from expected cosmic structure that we have ever found. When astronomer Robert Kirshner and his colleagues first mapped it in the early 1980s, the void was so anomalously large, so shockingly empty compared to what cosmological models at the time predicted, that there was genuine scientific unease about what it might mean. One of Kirshner's collaborators, in a moment of candour that has since become something of a legend in cosmological circles, reportedly said that if the Boötes Void were centred on the Milky Way, the nearest galaxy to us would still be outside it. We would look out from Earth into a sphere of nothingness 330 million light-years across and see nothing but darkness until we reached the wall on the far side. Sit with that for a moment, not as an abstract fact, as an experience. Imagine looking up at a night sky containing not a single point of light, not a single star in any direction, not even the faint smear of a distant galaxy at the limit of vision, just black, just void, just the humming, silent, impenetrable absence of everything. That is what the Boötes Void is. That is what we are exploring. And here is what should pull you forward into everything that follows. The Boötes Void should not exist. Not at its current size. Not at its current emptiness. According to the best cosmological models we had before the late 1990s, a void of that magnitude was effectively impossible. It was too large, too empty, too young to have formed through gravity alone in the time available since the Big Bang. Something else had to be involved, something that was not in the models, something that, when we finally identified it, turned out to be not just an explanation for the voids, but the dominant component of the universe itself. Something we still, despite decades of investigation, cannot explain, cannot detect directly, and cannot fully characterize. That something has a name, and its name is the beginning of a mystery so deep that it reaches from the largest structures in the observable universe all the way down into the fundamental nature of space itself. We will get there. But first, we need to understand how we found the voids in the first place, because the story of their discovery is itself a story of expectation colliding with reality in the most productive and unsettling way that science knows. For billions of years before any human eye looked upward, before any mind formed the concept of distance or emptiness or the space between things, the voids were there, growing, deepening, becoming what they are, and we had absolutely no idea they existed The reason for that ignorance is not a failure of intelligence or curiosity. It is a consequence of geometry. We live inside the universe we are trying to map, which means every observation we make is constrained by our position within it. For most of human history, we could not see far enough, could not resolve enough detail, could not distinguish between the darkness of empty space and the darkness of space that simply contained things too dim or too distant to detect. The voids hid in plain sight, indistinguishable from the rest of the night sky, waiting for us to develop instruments subtle enough to reveal their presence. The first serious attempts to map the three-dimensional distribution of galaxies in the universe began in the 1950s and accelerated dramatically in the 1960s and 70s. Before that point, most astronomical survey work was essentially two-dimensional. Telescopes could tell you where a galaxy appeared on the sky, its position in terms of right ascension and declination, the celestial equivalent of longitude and latitude. But position on the sky tells you nothing about distance. A galaxy that appears bright might be close and dim, or far away and luminous. Without distance measurements, you cannot build a map. You can only make a list. Distance measurement in astronomy is one of the great technical challenges of the field, and the methods used depend entirely on how far away the object is. For objects in our own solar system, radar works beautifully. You bounce a radio signal off the surface and measure how long it takes to return. For nearby stars, the technique of parallax works. As the Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. The size of that shift tells you the distance with good precision out to a few hundred light-years and with declining precision out to a few thousand. But galaxies are not a few thousand light-years away. Even the nearest large galaxy, Andromeda, is 2.5 million light-years distant. At those scales, parallax produces a shift so small it is undetectable, even with modern instruments. Something else is needed, and that something else was found in an unexpected place, in the properties of a particular type of pulsating star that would turn out to be one of the most important astronomical discoveries of the 20th century. Cepheid, variable stars are massive, luminous stars that pulsate in a remarkably regular way. They expand and contract, brighten and dim, with periods that range from roughly 1 day to roughly 100 days. In 1912, an astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory in a role that was officially classified as a human computer, rather than a scientist, because that was what institutions offered women with extraordinary gifts in that era, discovered something extraordinary about these stars. The period of their pulsation is directly related to their intrinsic luminosity. The longer the period, the brighter the star. This relationship is so precise and so consistent that if you measure how long a Cepheid takes to complete one pulsation cycle, you can calculate exactly how intrinsically luminous it is. Then you compare that intrinsic luminosity to how bright it appears in your telescope. The difference between how bright it is and how bright it looks tells you, through simple geometry, exactly how far away it is. Leavitt's discovery was the first reliable standard candle in astronomy, a way to measure cosmic distances that did not depend on assumptions or approximations, but on a physical relationship written into the stars themselves. Within a decade, Edwin Hubble was using Cepheids to establish that the Andromeda Nebula was not a cloud of gas within our own galaxy, but an entirely separate galaxy, millions of light-years away. That discovery alone restructured humanity's understanding of the cosmos more dramatically than any astronomical finding since Copernicus. But Cepheids have their own limitations. They are only detectable out to distances of roughly 100 million light-years, with the instruments available through most of the 20th century. Beyond that range, they become too dim to resolve individually. Something else was needed for greater distances, and that something else came in the form of a different kind of standard candle, one that would prove even more powerful, and whose behavior would eventually shatter the assumptions of an entire generation of cosmologists. Before we get to that, though, we need to return to the maps. Because the development of distance measurement techniques in the mid-20th century made it possible, for the first time, to do something genuinely new. To build a picture of the universe not as a flat projection of positions on the sky, but as a three-dimensional structure, a genuine map with depth showing not just where galaxies appeared, but where they actually were in the vast volume of space around us. The person who first pursued this vision with systematic rigor was a Harvard astronomer named Margaret Geller, along with her colleagues John Huchra and Valérie de Lapparent. In the 1980s, they undertook a project called the Center for Astrophysics Redshift Survey, which used the redshift of galaxies as a proxy for distance. Redshift works because the universe is expanding. Galaxies are generally moving away from us, and the farther away a galaxy is, the faster it is receding, and the more its light is shifted toward the red end of the spectrum by the Doppler effect. By measuring the redshift of a galaxy's light, you can calculate how fast it is receding, and from that recession speed, you can infer its distance. It is not a perfect technique. Galaxies also have their own local motions within clusters and groups, which add noise to the redshift signal. But for large-scale mapping purposes, redshift is extraordinarily powerful because it can be measured for thousands of galaxies in a relatively short time, with a moderately sized telescope. And what Geller, Huchra, and de Lapparent found when they mapped their first slice of the universe using this technique was so unexpected, so structurally dramatic, that when they presented their results, they reportedly compared the experience to opening a door and finding something completely different from anything on the other side. The universe was not uniformly distributed. It was not randomly scattered. It was not even approximately smooth. The galaxies were arranged in sheets and filaments and walls, great ribbons of matter stretching across tens of millions of light-years, surrounding enormous empty regions that contained almost nothing. The image that came from their survey, now known as the CFA2 Great Wall region, looked like nothing so much as the surface of foam. Thin walls of galaxies surrounding vast, round, relatively empty interior spaces. Structure on a scale nobody had fully anticipated, with a visual coherence, a pattern that was immediately recognizable even before any statistical analysis was done. This was the large-scale structure of the universe, the cosmic web, and the voids were its most dramatic feature. Now, here is the thing that makes this discovery particularly important for the story we are telling. The thing that sets up everything that follows in a way that cannot be fully appreciated without understanding the scientific context of that moment. In the 1980s, the dominant cosmological model predicted a universe that was, at large scales, fairly smooth. The structures were expected to exist, yes. Galaxies were known to cluster. Groups and clusters of galaxies were well established. But the scales of the structures Geller and her colleagues were finding were much larger than the models comfortably allowed. The voids were too big. The walls were too prominent. The universe was clumpier, more dramatically organized, more structured on large scales than the theory said it should be. This is the first major tension in our story. And tensions like this between what the theory predicts and what the observations show are the moments when science is at its most alive. They are the moments that either kill a theory or force it to evolve into something more powerful. In this case, the tension would not be resolved for another decade and a half, and the resolution would come from a completely unexpected direction, from astronomers studying not voids, but the deaths of stars in the distant universe, from a discovery so surprising that its implications are still being absorbed today. But before we follow that thread, let us go deeper into the voids themselves. Because the surveys of the 1980s were only the beginning, each generation of telescope and detector technology opened up new possibilities for mapping larger volumes of the universe with greater precision, and each new map revealed the voids in greater detail and with greater size than the previous generation had anticipated. The 2-degree field galaxy redshift survey completed in the early 2000s mapped over 200,000 galaxies across large portions of the sky. The Sloan Digital Sky Survey, which began around the same time and has continued in various phases since then, ultimately mapped hundreds of millions of galaxies and quasars across roughly 1/3 of the entire sky. These surveys did not just confirm the existence of voids, they revealed a hierarchy of voids, a nested structure in which smaller voids were contained within larger ones, and those within larger ones still all the way up to structures that strain the vocabulary of description. The largest individual void structures identified in modern surveys span hundreds of millions of light-years. Some reach toward 1 billion light-years across. These are not the largest structures in the universe in terms of total mass, because the voids contain very little mass. But in terms of geometric scale, in terms of pure spatial extent, they are among the most dramatic features in the observable cosmos. And their existence at those scales presented the same problem in a more acute form that the earlier surveys had first hinted at. How did structures this large form in the time available since the Big Bang? The answer, when it came, was elegant and devastating in equal measure. Gravity, working alone, pulling matter toward the dense regions and away from the underdense ones, could account for voids up to a certain size. Below that size, everything made sense. The math worked. The timescales were consistent, but above that size, gravity was not enough. Something was accelerating the evacuation of the voids, pushing matter outward from their centers faster than gravity alone could explain. Something was stretching the voids from the outside, pulling their walls apart at a rate that the known physics of the universe, gravity plus the known matter and radiation content, could not account for. That something had been hiding in the equations of general relativity since Einstein wrote them down in 1915. Einstein himself had added a term to his equations, a mathematical constant he called the cosmological constant, because without it his equations predicted a universe that was either expanding or contracting, and the universe of 1915 appeared to be neither. When Hubble's observations proved the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder and removed it from his equations. He thought the problem it was invented to solve did not exist. He was wrong about the problem not existing. He was wrong about the blunder. The cosmological constant, or something very much like it, turns out to be real. And its reality was demonstrated not by studying the voids directly, but by measuring the distances to exploding stars at the edge of the observable universe. In the late 1990s, 2 independent teams of astronomers set out to measure the rate at which the expansion of the universe was decelerating. Notice that word, decelerating, not accelerating. They assumed, as everyone assumed, as every model predicted, that gravity must be slowing the expansion down over time. The universe began with a bang. The matter within it exerts gravitational attraction on all other matter, and that attraction should be acting as a brake on the expansion, gradually slowing it over cosmic time. The question these teams were trying to answer was simply how strong that braking effect was. How much had the expansion slowed? They used a type of exploding star called a Type 1a supernova as their standard candle. These supernovae are caused by white dwarf stars, the dense remnants of medium-sized stars like our Sun that accumulate matter from a companion star until they reach a critical mass 1.4 times the mass of our Sun, and then detonate in a thermonuclear explosion of extraordinary power. Because every Type 1a supernova triggers at essentially the same critical mass, they all release essentially the same amount of energy, which means they all have essentially the same intrinsic luminosity. Point a telescope at a Type 1a supernova anywhere in the observable universe, measure how bright it appears, and you can calculate its distance with good precision. By measuring the distances and recession speeds of Type 1a supernovae at very large distances, the two teams expected to find that the supernovae were closer than a simple, constant expansion model would predict, because the expansion should have been faster in the past and should have been slowing down. A slower expansion today means the universe has not expanded as far as simple extrapolation would suggest, which means distant objects would appear slightly closer than expected. Instead, they found the opposite. The distant supernovae were farther away than expected. The universe was not decelerating. It was accelerating. The expansion of space was speeding up, and whatever was driving that acceleration was not behaving like any form of matter or energy that physics had ever characterized. Both teams published their results in 1998 and 1999. Saul Perlmutter, Brian Schmidt, and Adam Rees, the leaders of the two teams, would share the Nobel Prize in Physics in 2011 for this discovery. And the substance they discovered, or rather the gap in the ledger where they found something that could not be accounted for, was given a name that is both evocative and brutally honest about how little we understand it. Dark energy. Dark energy is whatever is driving the accelerating expansion. It is not dark in the sense of merely being unlit. It is dark in the sense of being completely undetectable by any instrument we have ever built or are likely to build. It does not emit light. It does not absorb light. It does not interact with matter in any way we can measure. It is characterized entirely by its effect on the expansion of the universe, an effect so powerful that it currently accounts for roughly 68% of the total energy content of the cosmos. 68%. More than 2/3 of everything, and we cannot tell you what it is. Now, look at the voids again, with this new understanding, because the voids are not incidental to the story of dark energy. They are central to it. They are the most direct, most unambiguous, most geometrically clear signature of dark energy's action on the structure of the universe. And this is why they are far more interesting than they first appear. Here is how it works. Dark energy, whatever it is, appears to be a property of space itself. It does not dilute as the universe expands the way matter and radiation dilute. As space expands, the dark energy within it does not spread out and weaken. It maintains a constant density, or something very close to constant, so that as the universe grows larger, the total amount of dark energy grows with it. This is deeply strange and has no analogue in ordinary physics. It is as if every cubic centimetre of empty space contains a fixed amount of energy, baked in, fundamental, not added, but intrinsic. In regions of space that are dense with galaxies and clusters, gravity is strong, and dark energy is fighting an ongoing battle against it. Matter pulls inward, dark energy pushes outward. In those dense regions, gravity is winning locally, which is why galaxies and clusters remain gravitationally bound, even as the universe overall expands. But in the voids, there is almost no matter. There is almost no local gravity to resist the outward push of dark energy. And so in the voids, dark energy acts almost unopposed. It drives the expansion of space within the void at full force, unimpeded, pushing the walls of the void outward, accelerating their recession from the void's center, making the void grow faster than gravity alone could account for. The voids are the places in the universe where dark energy is most dominant, where the ratio of dark energy to matter is highest, where its effects are most cleanly visible. And this makes the voids, counterintuitively, the best laboratories in the universe for studying what dark energy actually is and how it actually behaves. Think about that for a moment. The emptiest places in the universe are the most information-rich environments for answering the deepest question in modern physics. The places where nothing is are the places where the fundamental nature of space is most legible. We will follow that thread much further before we are done. But right now there is another aspect of the voids that deserves its own careful attention, because it connects not just to dark energy, but to a debate about the overall structure of the universe that is still unresolved, and that has implications far beyond what most discussions of cosmology ever reach. The voids are not randomly distributed. They are not scattered through the cosmic web like holes punched at arbitrary locations. They have a preferred size. They have a characteristic scale. And that characteristic scale, the typical diameter of a cosmic void before you start reaching the outliers and the giants, carries within it a message that was written into the universe just 380,000 years after the Big Bang. This message is called the Baryon Acoustic Oscillation Scale, and it is one of the most beautiful and powerful ideas in all of modern cosmology. To understand it, we need to go back to the early universe one more time, back to a moment when the cosmos was still a plasma of hydrogen and helium ions swimming in a sea of photons, and the future shape of everything had not yet been decided. In that young, hot universe, sound waves were propagating through the plasma, not metaphorical sound waves, actual pressure waves traveling through a medium just as sound travels through air. The medium was the hot plasma itself, and the pressure waves were driven by the same quantum fluctuations that eventually seeded the cosmic web. These waves had a finite travel speed, set by the temperature and density of the plasma, and they travelled outward from the density peaks, the slightly denser regions that would eventually become galaxy clusters. For 380,000 years, these sound waves travelled outward. Then something extraordinary happened. The universe cooled to the point where protons and electrons could combine to form neutral hydrogen atoms. This moment, called recombination, changed everything. When the plasma neutralized, it became transparent to light. The photons that had been trapped in the plasma, scattering endlessly off the charged particles, were suddenly free to travel unimpeded. They streamed outward and have been traveling through the universe ever since. We see them today as the cosmic microwave background, the oldest light in the universe, a faint glow of microwave radiation coming from every direction in the sky, a perfect snapshot of the universe as it was 380,000 years after the Big Bang. But when the plasma neutralized, it also ended. The medium in which the sound waves were traveling ceased to exist as a plasma. The sound waves froze. They stopped. At the moment of recombination, the wavefronts were located at a specific distance from the density peaks where they originated, a distance that can be calculated precisely from the physics of the early universe. That distance is approximately 490 million light-years in today's expanded universe, accounting for the stretching of space since recombination. Here is the beautiful part. When those sound waves froze, they left a ring of slightly enhanced density around every density peak, a shell, centered on each original fluctuation, with a radius of 490 million light-years. That shell contains slightly more matter than the average, which means slightly more galaxies will eventually form there. And the space just inside and just outside the shell, the void that sits inside each ring, and the slight underdensity just beyond it, carries the imprint of that ancient, frozen sound wave. We can measure this pattern today. When we analyze the distribution of galaxies across the sky, we find that galaxies are slightly more likely to be separated from each other by approximately 490 million light-years than by slightly smaller or slightly larger distances. This excess probability at that specific separation is the Borean acoustic oscillation signal, and it is one of the most powerful tools in cosmology because it provides an absolute, physically calibrated distance scale that we can use to measure the geometry of the universe and the behavior of dark energy across cosmic time. And the voids participate in this signal. The characteristic size of voids in the cosmic web is connected to the baryon acoustic oscillation scale. The pattern of empty spaces and filled spaces in the universe today carries within it the echo of pressure waves that traveled through the primordial plasma for 380,000 years and then stopped forever. The voids are not just empty, they are resonant. They ring with the encoded memory of the universe's infancy. Close your eyes for a moment and try to imagine what it would actually mean to be inside one, not near a void, not at the edge of one where the faint outlier galaxies thin out like the last trees at a timberline, actually inside, at the geometric center of something like the Boötes Void, a sphere of near total emptiness 330 million light-years across. You are there. Your hypothetical ship is stationary relative to the void's center, and you look out in every direction. In every direction, there is nothing. Not the nothing of a clear night sky between the stars, which is actually packed with structure, laced with the light of billions of distant galaxies crowded with the cosmic microwave background photons streaming through at the speed of light. This is a different kind of nothing. The nearest galaxies are so far away that their individual stars are not just invisible. They are not merely too dim to see with the naked eye. They are too dim to detect with any telescope that humanity has ever built, because they are not just far away in the ordinary astronomical sense. They are far away in the void sense, which is a different category entirely. The cosmic microwave background would still be there, coming from every direction, because it fills all of space. But its source, the surface of last scattering, is far behind the walls of the void. The walls themselves would appear as a faint, diffuse brightening in every direction. Not a sharp boundary, but a gradual transition from near total darkness to the faint glow of galaxies too distant and too spread out to resolve individually. From the center of the Boötes Void, the nearest substantial concentration of galaxies would be over 160 million light-years away in every direction. Light from those galaxies left them before the first complex animals evolved on Earth. It has been travelling through the void ever since, crossing the emptiness for longer than the entire history of multicellular life on our planet, and it is only now, in this hypothetical moment, reaching your eyes. You are not in darkness between things, you are in the void itself, which is a different existential condition. Everything that exists, every star, every galaxy, every nebula, every structure of any kind, is so far away that its gravitational influence at your location is essentially zero. The local geometry of space-time around you is as close to perfectly flat, perfectly empty, as any region in the observable universe gets. The expansion of space here is proceeding faster than anywhere else because nothing is pulling back against it. Dark energy owns this place. If you were somehow alive in this environment, and if you had a civilization, the night sky of your home world, if you had one, which you almost certainly would not because planets form around stars and stars do not live in void centers, would be nearly black. Not the rich black of an Earth night, salted with thousands of visible stars and striated with the Milky Way. Black. Perhaps a few dozen galaxies visible to an excellent instrument, dim smears at the limits of detection, all of them at distances measured in hundreds of millions of light-years. The universe would appear to be almost empty. And here is the haunting implication that should stop you. If your civilization arose inside a void, and if it was sufficiently isolated that it could not detect the distant galaxies beyond the void walls, you would have an extremely good chance of concluding that the universe was essentially empty. You would look out and see almost nothing. You might construct cosmological models that described a universe consisting almost entirely of space, with a sparse sprinkling of matter that was mostly concentrated in the small region you could observe. You would be profoundly wrong about the actual state of the cosmos, and you would have no way of knowing it from inside the void. This thought should do something to the confidence with which you hold any cosmological conclusion. Because we are also inside a structure, not a void. Our local environment is overdense, not underdense. We live in a region called the local group, which is itself part of a larger structure called the Virgo supercluster, which is itself part of an even larger structure called the Laniakea supercluster, a gravitationally defined region of space spanning roughly 500 million light-years and containing the mass of roughly 100 million billion suns. We are embedded in the cosmic web, surrounded by structure, not sitting in emptiness, but the principle holds. Our location in the universe shapes what we can see, and therefore shapes the cosmological models we construct. Astronomers have known this for decades, and it is why they work so hard to survey large enough volumes of the universe to see past local structure to the behavior of the cosmos as a whole. But knowing it intellectually is different from feeling it. The void thought experiment makes it feel real in a way that statistics cannot. And this brings us to one of the most unsettling debates in modern cosmology, one that the voids sit directly at the center of. It is a debate about whether the universe is the same in every direction on the largest scales, whether it has what physicists call isotropy and homogeneity, or whether there are genuine large-scale patterns and preferred directions in the structure of the cosmos that our models have not yet accounted for. The technical term for this assumption of sameness in all directions is the cosmological principle, and it is the foundational assumption of essentially all modern cosmology. If it fails, everything built on it needs to be reconsidered. The evidence for the cosmological principle is strong at scales above roughly 300 million light-years. At those scales and larger, the universe does appear smooth and uniform in every direction we look. Galaxy counts balance out. The distribution of matter and voids becomes statistically homogeneous. The cosmic microwave background is remarkably uniform in temperature across the entire sky, varying by only about 1 part in 100,000 in any direction, which is precisely what the cosmological principle predicts. But there are anomalies. There are features in the data that do not fit as cleanly as the standard model would like. The most dramatic of these, and the one most directly relevant to our journey through the voids, is a structure so large that its mere existence has generated sustained controversy among cosmologists for over a decade. It is called the cold spot, and it sits in the direction of the constellation Eridanus, in the southern celestial hemisphere. The cold spot is a region of the cosmic microwave background that is slightly cooler than its surroundings, roughly 70 microkelvins cooler than the average temperature of the background radiation. That difference sounds trivially small, but in the context of the cosmic microwave background, which varies by only about 1 part in 100,000 across the entire sky, a deviation of that magnitude at the angular scale of the cold spot is statistically very unlikely under standard cosmological assumptions. What makes the cold spot relevant to the voids is what lies in front of it, between us and the surface of last scattering from which the cosmic microwave background originates. In the direction of the cold spot, there is a supervoid, a vast underdense region of space spanning roughly 1.8 billion light-years, centered approximately 3 billion light-years from Earth, containing significantly fewer galaxies than surrounding regions of equivalent volume. This structure is sometimes called the Eridanus supervoid, and its existence raises an obvious question. Is the cold spot caused by the supervoid? Did light traveling through that enormous void lose energy in a way that made it arrive at us slightly cooler than light that traveled through denser regions? The mechanism by which this could happen is called the integrated Sachs-Wolf effect, named for the two physicists who first described it in 1967. In a universe without dark energy, a photon falling into a gravitational potential well, a dense region, would gain energy and then lose exactly that energy when climbing out the other side, leaving its net energy unchanged. But in a universe with dark energy, the potential wells themselves are changing while the photon is crossing them, because the accelerating expansion is continuously reshaping the gravitational landscape. The result is that photons crossing large underdense regions, voids, lose a small amount of energy that they do not fully recover, arriving at the observer very slightly cooler than they would have been otherwise, and photons crossing large overdense regions gain a small net energy, arriving slightly warmer. This is, in principle, exactly the mechanism that could produce the cold spot. A photon streaming toward us from the surface of last scattering, passing through a supervoid of the scale and depth of the Eridanus supervoid, would lose a small amount of energy in transit. The question is whether the supervoid is deep enough and large enough to produce the full magnitude of the cold spot we observe. The honest answer, based on the best analyses available, is probably not quite. The Eridanus supervoid is large enough and empty enough to produce some of the cold spot signal, but the numbers suggest it cannot account for all of it. Whether the remainder represents a genuine cosmological anomaly, a rare but not impossible fluctuation in the standard model, or evidence for something more exotic, is a question that remains genuinely open. Different research groups analyzing the same data have reached different conclusions, which is itself a sign that the question is at the frontier of what current observations can definitively resolve. But the cold spot controversy points towards something larger than itself. It illustrates the fact that the voids are not just passive witnesses to cosmological processes. They actively shape the light that passes through them. They modify the temperature of the cosmic microwave background in ways that depend directly on the properties of dark energy. They are, in other words, a tool for measuring dark energy that works on scales and through mechanisms completely different from the supernova observations that first revealed dark energy's existence. This is worth pausing to appreciate. We have two completely independent methods of detecting and characterizing dark energy. One looks at the distances and recession speeds of exploding stars at the far edges of the observable universe. The other looks at the temperature patterns imprinted on the oldest light in the universe by the voids through which it has traveled. These two methods should give consistent results if our model of dark energy is correct. And for the most part, they do. But there are tensions, small discrepancies, places where the numbers do not quite line up. Those discrepancies might be measurement errors. They might be systematic biases in the instruments or analysis techniques, or they might be signals. They might be the universe telling us that our model of dark energy is not quite right, that the cosmological constant is not precisely constant, that dark energy evolves over time, or that the physics of the early universe differs in some subtle way from what we have assumed. The voids are one of the sharpest tools we have for investigating this question, and several major astronomical surveys underway right now, including the Dark Energy Spectroscopic Instrument, which began its main survey in 2021 and is mapping tens of millions of galaxies with extraordinary precision, are specifically designed to use the statistical properties of voids and the baryon acoustic oscillation signal to constrain the behavior of dark energy across cosmic history with unprecedented accuracy. The results from these surveys are already beginning to arrive, and they are doing exactly what the best results always do. They are answering some questions and opening others. We will come back to those results because they carry implications that reach far beyond the technical parameters of any individual survey. But first, there is a dimension of the voids that we have not yet examined, one that most discussions of large-scale structure skip entirely because it seems at first like a digression. It is not a digression. It is one of the most fascinating aspects of void science, and it connects the enormous cosmic scale of the voids to something much closer to home. Something that affects every galaxy in the universe, including the one we live in. Something that explains why the Milky Way is where it is, moving the way it is moving in the direction it is heading. The Milky Way is not stationary. We know this in multiple senses. The Earth orbits the Sun. The Sun orbits the center of the Milky Way, completing one full orbit roughly every 225 million years at a speed of about 220 kilometers per second. The Milky Way itself moves within the local group, and the local group moves through the larger cosmic web. All of this motion is layered, nested, simultaneously occurring across different scales. But there is a component of our motion that puzzled astronomers for decades. When you subtract all the known, explicable components of our velocity, what remains is a residual motion. The Milky Way, along with the entire local group, is moving toward a particular region of the sky at a speed of roughly 630 kilometers per second. This motion cannot be explained by the gravitational attraction of any nearby structure we can directly observe. It has a name. It is called the peculiar velocity, specifically the component of our peculiar velocity that points in the direction of the constellation Centaurus. For a long time, the source of this pull was mysterious. The region toward which we were moving was obscured by the dust and gas of the Milky Way itself, which blocked our view of the galaxies behind it in a region astronomers call the zone of avoidance. When surveys finally managed to peer through the zone of avoidance using infrared light and radio waves, which penetrate dust more effectively than visible light, they found what they were looking for. A massive concentration of galaxies, a supercluster region centered on an object called the Great Attractor, located roughly 150 million light-years away in the general direction of the Centaurus and Hydra Centaurus constellations. But even the Great Attractor, massive as it is, did not fully account for our motion. There was still a residual, still something pulling us in a direction that no identified structure could explain. Investigations continued, surveys expanded, and eventually a more complete picture emerged. We are being pulled toward a massive concentration of matter, yes, but we are also being pushed away from a massive concentration of emptiness, the dipole repeller. Identified in 2017 by a team led by Yehuda Hoffman at the Hebrew University of Jerusalem, the dipole repeller is a supervoid located in roughly the opposite direction from the Great Attractor. It spans hundreds of millions of light-years and is significantly underdense compared to its surroundings. And, because an underdense void has less gravitational pull than average on the galaxies around it, it effectively pushes those galaxies away in the sense that the matter surrounding the void falls into the denser regions on the other side, creating what looks from the perspective of the galaxies near the void like a repulsive force. The Milky Way is caught between a pull and a push. We are being gravitationally attracted toward the massive structure in one direction and simultaneously being pushed in the sense of being less strongly attracted in the opposite direction, away from the void behind us. These two effects combine to produce the peculiar velocity we observe. And without understanding the void, without accounting for the dipole repeller, the motion of our own galaxy was inexplicable. This is the moment in the story where the voids stop being abstract, cosmological features and become personal. The void is not out there, unrelated to us. The void, or rather the absence of gravitational attraction associated with the void, is one of the forces shaping the trajectory of our galaxy through space. We are being steered in part by emptiness. The implications of this extend further than our individual galaxy. The cosmic web, with its filaments and walls and clusters and voids, creates a velocity field across all of space. Every galaxy is moving not just due to the expansion of the universe, but due to the gravitational influence of every overdense and underdense region around it. The galaxies flow along the filaments towards the clusters. They pour out of the voids and into the walls. The motion of matter in the universe is not random or isotropic. It is organized, channeled, directed by the topology of the web itself. And that topology, that specific arrangement of structures and voids, carries information. Information about the initial conditions of the universe, information about the nature and strength of dark energy, information about the total amount of matter in the cosmos, both the ordinary matter we can see and the dark matter we can only infer from its gravitational effects. Everything about the large-scale structure of the universe, including the detailed geometry of the voids, is a consequence of the initial conditions and the physical laws that governed the evolution of those conditions. If you could perfectly map the cosmic web and perfectly understand the physics, you could read the initial conditions of the universe directly from the structure you observe today. We cannot do this perfectly. Our maps are incomplete, our measurements have errors, and our theoretical understanding of the physics is good but not flawless. But we are getting better. Each generation of survey goes deeper, covers more sky, measures more galaxies, constrains the models more tightly, and the voids are among the cleanest, most information-rich features in those surveys precisely because they are so empty. In a dense galaxy cluster, the physics is complicated by hydrodynamics, by feedback from supermassive black holes, by the complex interactions between gas and stars and dark matter. In a void, there is almost none of that complexity. The physics of a void is dominated by gravity and dark energy, which are the two things we most want to understand. There is another layer to the story of voids and information that connects to something we mentioned briefly earlier and must now develop fully. Because the voids have a characteristic scale, that approximately 490 million light-year baryon acoustic oscillation scale, they can be used as a standard ruler in a way that is complementary to the supernova standard candle. If you know the true physical size of a feature in space, and you can measure both its angular size on the sky and the recession speed associated with it, you can calculate the geometry of the space between us and that feature. And from the geometry, you can infer the history of the expansion of the universe, and from the expansion history, you can characterize the behavior of dark energy over cosmic time. This is the essence of void cosmology as a precision measurement tool. The voids are not just interesting for what they are. They are interesting for what they let us measure about the universe as a whole. Every well-characterized void is a data point in the determination of some of the most fundamental parameters in physics. The equation of state of dark energy, which describes how its energy density changes with the expansion of the universe, the total matter density of the cosmos, the Hubble constant, that foundational number that describes how fast the universe is expanding today, which is currently at the center of one of the most significant tensions in modern cosmology, the Hubble tension. We should spend a moment here because it is directly relevant to what the voids are teaching us and because it is one of the most important unresolved puzzles in contemporary physics. The Hubble constant can be measured in two fundamentally different ways. You can measure it locally by calibrating distances using Cepheid variables and Type 1a supernovae in the relatively nearby universe, and then measuring the recession speeds of galaxies at those distances. Or you can measure it from the early universe by analyzing the detailed pattern of the cosmic microwave background and extrapolating forward to the present using the standard cosmological model. These two methods should give the same answer if the standard model is correct. They do not. The local measurements consistently give a Hubble constant of around 73 kilometers per second per megaparsec, meaning that for every megaparsec of distance between us and a distant galaxy, that galaxy is receding roughly 73 kilometers per second faster due to the expansion of space. The early universe measurements consistently give a value of around 67.4 kilometers per second per megaparsec. The discrepancy is roughly 8 to 9%. That might sound small, but in the context of precision cosmology, it is enormous. It has persisted through multiple independent analyses, multiple different observational approaches, and multiple generations of increasingly precise data. Either the measurements have systematic errors that nobody has yet identified, which is possible but increasingly unlikely, given how many independent groups have checked their work, or the standard cosmological model is missing something. Something happens between the early universe and today that the model does not account for, something that caused the expansion to proceed at a rate not fully predicted by extrapolating the early universe measurements forward. The voids are relevant to this tension because void statistics provide yet another independent measure of cosmological parameters that can be compared to both the local and early universe values. Early results from void analyses in the Sloan Digital Sky Survey and other large catalogues have generally been consistent with the early universe value, which, if correct, would suggest that the tension lies in the local measurements rather than in the cosmology, but the precision of void-based measurements is still improving, and as the new generation of surveys comes online, the void statistics will become a genuinely powerful third independent constraint on the Hubble constant. If they break clearly toward one value or the other, that will be significant evidence about where the discrepancy actually lies. What does it mean if the standard model is genuinely wrong? What does it mean if there is missing physics between the early universe and today? It could mean many things. It could mean that dark energy is not a cosmological constant, but a field, something that evolves over time that was weaker in the early universe and stronger now, or vice versa. It could mean that there was an additional component of energy in the early universe that decayed away before recombination, something called early dark energy, that temporarily altered the expansion rate in a way that left its fingerprints in the Hubble tension. It could mean that gravity itself behaves differently on cosmological scales than general relativity predicts. That Einstein's equations, which have passed every test we have ever applied to them in the solar system and in compact objects like neutrons, stars, and black holes, begin to break down when applied to the universe as a whole. Each of these possibilities has implications that extend far beyond cosmology. They touch the foundations of physics. They raise questions about whether the laws we have derived from observations in our local cosmic neighborhood apply universally, across all scales and all epochs. The voids, by virtue of being the cleanest probes of dark energy and geometry that nature provides, sit at the center of this investigation. And there is one more dimension of the voids that we need to introduce before we can bring all of these threads together. It is the most counterintuitive aspect of void science, the one that most directly inverts our usual assumptions about where interesting things happen in the universe. It is the question of what is actually inside the voids, not what is absent, but what, against all expectation, is present. This statement deserves to land before we try to qualify it, because the qualification that follows does not diminish the emptiness so much as it reveals something even stranger about what emptiness actually means at cosmic scales. When we say the voids are not perfectly empty, we do not mean they contain hidden clusters of galaxies that our surveys missed. We do not mean that the darkness resolves into structure if you look closely enough. We mean something more subtle and more profound than that. We mean that the voids contain matter, but that matter is itself a revelation about the processes that shaped the universe and about the future that awaits everything within it. Start with the galaxies. There are galaxies inside voids. Not many, not enough to challenge the characterization of voids as the emptiest regions of the cosmic web, but they are there, scattered across the interior like the last few inhabitants of an evacuating city, and they are not ordinary galaxies. They are different from the galaxies that live in filaments and walls and clusters in ways that tell us something important about how environment shapes the evolution of matter over cosmic time. Void galaxies, as they are called, tend to be smaller. They tend to be bluer. They tend to be actively forming new stars at rates proportionally higher than comparable galaxies in denser environments. And they tend to be more isolated, more undisturbed, more pristine in a certain sense because they have not experienced the mergers and interactions and ram pressure stripping and tidal disruptions that shape and reshape galaxies in crowded environments over billions of years. A galaxy in a cluster has had a violent history. It has been pulled by the gravity of its neighbours, stripped of its outer gas by the hot intra-cluster medium, harassed by repeated close encounters with other galaxies, possibly merged with one or more companions over the course of its existence. Its star formation history is complicated, shaped as much by external forces as by its own internal physics. It is a galaxy that has been profoundly affected by its environment. A void galaxy has largely been left alone. It formed from the sparse material available in the underdense region it inhabited, grew slowly without significant mergers, retained its gas because there was nothing to strip it away, and has been forming stars at a steady if modest rate throughout much of its history. It is, in a real sense, a simpler object, and simpler objects are easier to understand. By studying void galaxies in detail, astronomers can isolate the intrinsic physics of galaxy formation and evolution from the complicated environmental effects that dominate in denser regions. The void galaxies are the control group in a cosmic experiment that we did not design but are fortunate enough to be able to observe. The differences between void galaxies and cluster galaxies also encode information about the timeline of structure formation. The fact that void galaxies are still forming stars, still blue and active, while many cluster galaxies have long since exhausted their gas and become red and quiescent, tells us something about when and how efficiently star formation shuts down in different environments. Tracing that process across different environments, from the densest clusters to the emptiest voids, is one of the central projects of modern galaxy evolution research. But the galaxies are not the most interesting thing inside the voids, or rather, they are not the most cosmologically significant thing. The most significant thing is something you cannot see with any telescope. It is not matter in any form that emits or absorbs light. It is the dark matter. Dark matter is not dark energy. This distinction matters and is frequently confused in popular discussions. Dark energy is the mysterious component that drives the accelerating expansion of the universe. Dark matter is a completely separate mystery, a form of matter that does not interact with light in any way we can detect, that passes through ordinary matter with negligible interaction, but that has mass and therefore exerts and responds to gravity. Dark matter was first inferred from observations of galaxy rotation curves in the 1960s and 70s, from the observed fact that the outer regions of galaxies rotate faster than can be explained by the visible matter alone. The only way to account for those rotation speeds is to posit that galaxies are embedded in enormous halos of invisible mass, extending far beyond the visible disk. Subsequent observations confirm this inference from multiple independent directions. The gravitational lensing of light by galaxy clusters shows more total mass than the visible matter can account for. The temperature distribution of hot gas in galaxy clusters indicates a gravitational potential far deeper than the visible galaxies can produce. The pattern of the cosmic microwave background, which depends sensitively on the total matter content of the early universe, requires a matter component roughly 5 times more abundant than ordinary atomic matter. Everything points in the same direction. Roughly 84% of the matter in the universe is dark matter. The ordinary matter we can see, the atoms, the molecules, the stars, the gas, the dust, everything that has ever been touched or photographed or measured by any instrument humanity has ever built, constitutes only about 16% of the total matter budget. And that total matter budget is itself only about 32% of the total energy content of the universe, with dark energy making up the remaining 68%. Think about what this means. The universe as we experience it, the universe of stars and galaxies and light and matter that can be touched and analyzed, the universe that all of science before the late 20th century was studying, is roughly 5% of the total content of the cosmos. The other 95%, 84% dark matter and 68% dark energy as fractions of the total, is invisible, undetected in any direct sense, and understood only through its gravitational and geometric effects. We live in a cosmos that is 5% legible and 95% dark. Now, bring this back to the voids. The dark matter is not uniformly distributed any more than ordinary matter is. It traces the same large-scale structure, the same cosmic web of filaments and walls and clusters, though with somewhat less dramatic contrast, because dark matter does not form stars or emit light and therefore behaves somewhat differently than the gas that eventually forms galaxies. But in the voids, the dark matter is as absent as everything else. The underdense regions that contain few galaxies also contain little dark matter. The dark matter, like the ordinary matter, has flowed out of the voids over cosmic time, pulled toward the surrounding walls and filaments by the same gravitational gradients. What remains in the voids in terms of dark matter is a sparse, nearly uniform background of dark matter particles, not enough to significantly alter the gravitational dynamics of the void interior, not enough to stop the void from expanding, but enough to create a very faint web of structure, even within the void. The voids are not perfectly uniform internally. They have their own internal structure, their own subvoids and subfilaments at much smaller scales than the primary void. This internal structure, sometimes called the void interior morphology, is one of the active frontiers of observational and computational cosmology, and there is something extraordinary hiding in the void interior morphology, something that simulations of dark matter structure formation have been predicting for decades and that observations are only now beginning to confirm at sufficient precision to be scientifically useful. Inside the voids, threading through the dark matter background, there are sheets and tendrils of slightly enhanced dark matter density. These are the remnants of the original small-scale structure that seeded the void before it was evacuated. The void is not a perfectly smooth sphere of emptiness. It is a slightly lumpy emptiness, with internal structure that echoes at smaller scales the same web topology that defines the cosmos as a whole. The void is a universe in miniature. The cosmic web has voids, and the voids have their own internal web. The pattern repeats, nested, self-similar across scales, not perfectly fractal, because the physics changes at different scales, but remarkably consistent in its qualitative character. Filaments and walls and voids at every scale, from tens of millions of light years down to the smallest structures that dark matter halos can support, which is somewhere around the scale of dwarf galaxies or below, depending on the nature of the dark matter particle. That last phrase, the nature of the dark matter particle, opens one of the deepest questions in contemporary physics, one that the void interior morphology is directly relevant to. We do not know what dark matter is made of. We have strong constraints on what it is not. It is not ordinary atoms, not neutrons, not protons, not any particle in the standard model of particle physics. It is not black holes of the mass ranges most comprehensively searched. It is not neutrinos, the ghostly lightweight particles that do interact weakly with matter and are abundant in the universe but whose properties make them the wrong candidate to account for the observed structure of the cosmic web. The leading candidates fall into broad categories. The most extensively searched category consists of weakly interacting massive particles, or WIMPs. Hypothetical particles with masses in the range of 10 to a few thousand times the mass of a proton that interact with ordinary matter only through gravity and the weak nuclear force. WIMPs are theoretically appealing because they arise naturally in several extensions of the standard model of particle physics, and because they would have been produced in exactly the right abundance in the early universe to account for the observed dark matter density. Decades of experiments in underground laboratories, particle colliders, and space-based detectors have searched for WIMPs with increasing sensitivity. So far, nothing. The null results have ruled out large regions of the parameter space where WIMPs were expected to live, forcing theorists to consider either that WIMPs exist, but at properties different from those originally predicted, or that the dark matter consists of something else entirely. The something else is a rich menagerie of theoretical possibilities. Axions, extremely light particles originally proposed to solve a problem in the theory of the strong nuclear force, have become increasingly compelling dark matter candidates. Sterile neutrinos, hypothetical cousins of the ordinary neutrino that interact only through gravity, are theoretically motivated by the observed fact that ordinary neutrinos have mass, which the original standard model did not predict. Primordial black holes formed in the very early universe before any stars existed, have attracted renewed attention, though observations constrain how much of the dark matter they could constitute. The void interior morphology is relevant to all of these candidates because different dark matter particles produce subtly different small-scale structures. A universe of heavy WIMPs produces slightly different void interiors than a universe of ultra-light axions. The detailed statistics of subvoid structure, if measured precisely enough, can in principle discriminate between dark matter candidates that are otherwise indistinguishable from each other on large scales. This is one of the reasons that the next generation of surveys, which will map the positions of billions of galaxies with extraordinary precision, including the sparse void galaxy populations, represents such a significant advance in dark matter physics as well as in dark energy cosmology. But we have been circling around something, and it is time to face it directly. Something that has been implicit in everything we have discussed, that has been building beneath the surface of the narrative since we first described the quantum fluctuations of the infant universe and the formation of the cosmic web. Something about the future, something about what happens to the voids and to everything else over time scales that dwarf anything we have considered so far. The universe is accelerating. We have established this. Dark energy is driving the expansion of space faster and faster over time. What does this mean for the future of the cosmic web? What does it mean for the voids, which are already the regions where dark energy is most dominant? And what does it mean, ultimately, for the galaxies and stars and any possible future observers that might exist in the cosmos billions and trillions of years from now? The answer to these questions is one of the most profound and, in a certain sense, one of the most melancholy things that cosmology has discovered in the modern era. And it requires us to extend our perspective not just billions, but trillions and quadrillions of years into the future, into a realm of time so vast that the current age of the universe is not even a rounding error compared to the timescales involved. In the relatively near future, cosmologically speaking, meaning over the next few tens of billions of years, the accelerating expansion will do something specific and measurable to the cosmic web. The voids will continue to grow. The walls and filaments will continue to drain into the clusters. The large-scale structure will become more extreme, more differentiated, with the overdense regions becoming more concentrated and the underdense regions becoming more empty. The cosmic web will sharpen rather than smooth out because dark energy is not just expanding the universe uniformly, but is specifically evacuating the voids faster than gravity is being overcome by it elsewhere. On a timescale of roughly 100 billion years from now, the expansion of the universe will have proceeded to the point where galaxies outside the local group will have receded beyond a distance called the cosmological event horizon. This is the distance beyond which the recession speed of space exceeds the speed of light, which means light emitted from beyond that horizon can never reach us, no matter how long we wait. The universe beyond the cosmological event horizon is causally disconnected from us. It might as well not exist from our perspective. Today, the cosmological event horizon is roughly 16 billion light-years away. The observable universe, the region from which light has had time to reach us since the Big Bang, extends to about 46 billion light-years. The event horizon is already well inside the observable universe. Galaxies are already receding beyond it, but the number of galaxies we can see in principle is still enormous, roughly 2 trillion galaxies in the observable volume. As the expansion accelerates, the event horizon will contract relative to the positions of distant galaxies. More and more galaxies will slip beyond it, their light redshifting to longer and longer wavelengths until it becomes undetectable, their apparent positions freezing and fading as their light signals can no longer reach us. A future civilization in the Milky Way, 100 billion years from now, will observe a universe that appears nearly empty. The local group will have merged into a single large elliptical galaxy. Beyond it, there will be almost nothing visible. The vast cosmic web, the galaxy clusters and superclusters and filaments that surround us today, will have vanished beyond the event horizon, invisible, inaccessible, effectively gone. That future civilization, if it exists and if it attempts cosmology, will face a situation similar in some ways to the hypothetical void civilization we imagined earlier, but different in a crucial respect. The void civilization was in a genuinely empty region of space. The future civilization will be in what was once a very rich region, but the universe will have expanded beyond its observational reach. It will look out from what was once the heart of Laniakea supercluster and see emptiness not because emptiness is there, but because the fullness has receded beyond the speed of light. They will have no way of knowing this from observation alone. The cosmic microwave background will have redshifted to wavelengths thousands of times longer than it exhibits today, essentially undetectable with any conceivable instrument. The baryon acoustic oscillation signal in the galaxy distribution will be invisible, because there will be no observable galaxies beyond the local group remnant. The evidence for the Big Bang, for the cosmic web, for the entire grand structure of the universe we are mapping today will be gone, erased not by any catastrophe but by the simple, relentless expansion of space. We are extraordinarily lucky to exist at this moment, not just in the sense of biological fortune, though that is also true. Lucky in the sense that we exist at the one epoch in the history of the universe when both the early universe evidence in the form of the cosmic microwave background and the large-scale structure evidence in the form of the cosmic web with all its galaxies and voids are simultaneously observable. Earlier, the structure had not yet fully developed. Later, the structure will have receded beyond observational reach. Right now, and for perhaps a few tens of billions of years more, the universe is maximally legible. We are observing it at the moment when it reveals the most about itself, and yet within that maximally legible universe, the voids are expanding, right now. The walls of the Boötes Void are receding from its center. The interior of the Eridanus supervoid is becoming emptier as matter continues to flow outward along the gravitational gradients toward the surrounding structures. The voids are not static features of the cosmic landscape. They are dynamic, growing, deepening, occupying an ever larger fraction of the total volume of the universe. Already, the voids occupy roughly 80% of the total volume of the observable universe. The cosmic web, with all its galaxies and clusters and filaments, the entire visible structure of the cosmos, is confined to roughly 20% of the total volume. The universe is, by volume, mostly void. It is mostly emptiness, mostly the dark space between the structures, mostly the domain where dark energy reigns unopposed and space expands fastest. This fraction will increase. The voids will grow. The structures will become more concentrated into a smaller fraction of the total volume, even as they become denser internally. The universe is evolving toward a state of increasing contrast, increasing differentiation, with matter more and more tightly clustered in isolated islands, separated by ever larger oceans of expanding void. And on timescales far longer even than this, on timescales measured in trillions and quadrillions and unimaginably larger numbers of years, the isolated islands themselves will dissolve. The stars will exhaust their fuel and die. New star formation will eventually cease as the gas that feeds it is consumed or dispersed. The stellar remnants, white dwarfs, and neutron stars and black holes will gradually evaporate through quantum mechanical processes that operate on timescales of 10 to the power of 67 years and longer. The black holes themselves will evaporate through Hawking radiation on timescales of 10 to the power of 67 to 10 to the power of 100 years, depending on their mass. At the very end, if the laws of physics as we understand them continue to hold, the universe will consist of nothing but a cold, dark, expanding void. Not the void of the cosmic web, which is a relative emptiness defined in contrast to the surrounding structure. The void of thermodynamic death. The maximum entropy state. The condition in which no further work can be done, no further structure can form, no further information can be processed. An eternal, featureless expansion into a future indistinguishable from the past. This is the fate that current physics points toward. And the voids, the great empty regions we have been exploring throughout this journey, are the previews of that fate. They are the nearest approximation existing in the present universe of what all of space will eventually become. The void is not just an emptiness in the current structure, it is a glimpse of the final state of the cosmos. But here is the pivot that changes everything, the recontextualization that this entire journey has been building toward, because the fate of the universe depends entirely on what dark energy actually is. And dark energy, as we have established, is the one quantity that the voids can measure with the most precision and the most clarity of any environment in the observable cosmos. The voids are not just witnesses to the fate of the universe, they are the instruments by which we will determine what that fate actually is. We have travelled a long way together through the dark. We started in the quantum foam of the universe's first moments, where fluctuations smaller than any atom were being stretched by inflation to cosmic scales. We watched gravity work its patient, relentless arithmetic across billions of years, pulling matter toward the dense regions and draining it from the sparse ones, sculpting the cosmic web from an almost featureless beginning. We stood at the center of the Boötes Void and felt the weight of 330 million light-years of nothing pressing in from every direction. We traced the baryon acoustic signal, that frozen echo of primordial sound, through the statistical distribution of galaxies and voids across the observable universe. We followed the peculiar velocity of our own galaxy and found that we are being steered in part by the gravitational absence of a supervoid behind us. We looked forward into deep time and watched the voids grow, the structures concentrate, the observable universe contract toward a final cold silence. And through all of it, the same question has been circling, not the technical question of what dark energy is, though that question matters enormously, something deeper, something that the journey through the voids has been preparing us to ask properly. What does it mean that we can know any of this? Hold that question for a moment. Do not let it dissolve into abstraction before it has a chance to land, because it is genuinely extraordinary in a way that familiarity with science can sometimes blunt, that a species of medium-sized mammals on a rocky planet orbiting an undistinguished star in the outer regions of one galaxy among 2 trillion has managed to reconstruct the history of the universe from its first fraction of a second to its eventual thermodynamic dissolution. That we have found the frozen sound waves from the infant cosmos imprinted in the distribution of galaxies. That we have detected the influence of quantum fluctuations from before the first microsecond of time in the temperature map of the oldest light we can observe. That we have identified the force driving the expansion of space by measuring the brightness of exploding stars billions of light-years away. This is not ordinary. This should not be taken as ordinary. The capacity to do this, to reach out from a small, warm, biology-covered rock and reconstruct the shape and history and likely fate of the entire cosmos, is something that, as far as we know, has never happened before in the history of the universe, not because we are special in any grandiose sense, but because we are here, and we are looking, and we have developed the tools and the language and the collaborative institutions that allow the looking to accumulate into understanding over generations. The voids are the context for this appreciation, because the voids are what most of the universe looks like. Most of the universe is not the Milky Way, not the local group, not the warm, structured, matter-rich environment that allowed stars to form and planets to coalesce and chemistry to complexify into biology and biology to develop nervous systems capable of asking questions about the void. Most of the universe is the void itself. Dark, cold, expanding, empty, structureless, incapable of supporting any of the processes that led to us. We exist in the rare exception, in the thin filaments and walls of the cosmic web, in the dense but still structured environments where gravity was strong enough to overcome the expanding void and gather matter into the concentrations that allow complexity. We are, in a real and measurable sense, the product of the overdense regions, the places where the quantum fluctuations of the early universe happened to be slightly positive rather than slightly negative, where gravity won the local contest against expansion, where the conditions existed for matter to organize itself into increasingly intricate structures over billions of years. The void is not our origin, but understanding the void is essential to understanding our origin, because the void and the structure are the same thing seen from different angles. They are the two faces of the same process, the same initial conditions expressed through the same physical laws in complementary ways. You cannot understand why galaxies exist without understanding why voids exist. You cannot understand why stars form without understanding why most of space is too empty for star formation. You cannot understand why we are here without understanding why almost everywhere is the kind of place where we could not be. This is the insight that the void offers that no other environment in the universe provides so cleanly. The void is the negative space that defines the shape of the positive. It is the silence that gives the music its form. And we have spent billions of years, the age of our solar system, embedded in the music close enough to hear it and feel it and be made of it, but until very recently without the capacity to step back far enough to see the silence that surrounds it. The development of large-scale structure surveys, the realization that the universe has a cosmic web, the identification of the supervoids and their role in shaping the distribution of matter and the properties of the cosmic microwave background, all of this represents a genuine expansion of human perspective. Not just in the sense of adding new facts to an existing picture, but in the sense of changing the picture itself. The universe we understand today is a fundamentally different object from the universe as it was understood a century ago, not because the universe changed, but because our picture of it finally became large enough to contain its most dramatic features, and the picture is still growing. The surveys underway right now, the Dark Energy Spectroscopic Instrument, the Euclid Space Telescope launched in 2023, the Vera C. Rubin Observatory beginning its legacy survey of space and time, the Nancy Grace Roman Space Telescope planned for the coming years. These instruments are not minor refinements of what came before. They represent qualitative leaps in our ability to map the large-scale structure of the universe, including the voids, with a precision that will either confirm the standard cosmological model with extraordinary accuracy or reveal the cracks in it with sufficient clarity to force a genuine revision of our understanding of the cosmos. The Euclid mission deserves particular attention in this context because its primary scientific goals are so directly connected to everything we have discussed. Euclid is designed to measure the shapes of roughly 1.5 billion galaxies across more than a third of the sky, out to redshifts corresponding to roughly 10 billion years in the past. From those shape measurements, it will extract the weak gravitational lensing signal, the tiny, correlated distortions in galaxy shapes caused by the gravitational influence of all the matter, dark and ordinary, between us and those galaxies. And from the distribution of those galaxies in 3 dimensions, it will measure the baryon acoustic oscillation scale with extraordinary precision at multiple epochs in cosmic history. The void statistics from Euclid will be transformative. With 1.5 billion galaxies mapped across such an enormous volume, the number of well-characterized voids in the catalogue will be in the millions. The statistical power of millions of voids, each one a measurement of the geometry of space and the behavior of dark energy at its location and epoch, will be orders of magnitude greater than anything available from previous surveys. If dark energy is not a pure cosmological constant, if it evolves over time even slightly, Euclid's void statistics will see it. If the Hubble tension reflects a genuine failure of the standard model rather than a measurement systematic, the combination of Euclid's data with other surveys will have the power to identify where the failure occurs. This is science at its most ambitious and most honest. Not claiming to have all the answers, but building the instruments that have the power to distinguish between possible answers with sufficient precision that the universe itself can adjudicate. The void is the laboratory, the question is fundamental, and the experiments are running right now. Their data accumulating in real time, the analysis pipelines processing it, the results beginning to emerge. Some of those results are already causing careful attention. Early data from the Dark Energy Spectroscopic Instrument released in 2024 showed mild but interesting tensions with the standard cosmological model when the baryon acoustic oscillation measurements were analyzed across different redshift bins. The dark energy equation of state parameter, which in a pure cosmological constant model should be exactly -1, showed hints of deviation, not statistically conclusive, not at the level that would overturn the model, but present, persistent, across multiple analysis approaches, and consistent with a class of dark energy models in which the energy density of dark energy was higher in the past and is declining toward a constant value in the present. If this hint strengthens as more data arrives, it would have profound implications. A dark energy that evolves over time is not a cosmological constant. It is a field, something with dynamics, something that changes as the universe evolves. A field has implications for the eventual fate of the universe that differ from those of a true constant. A field can in principle decay. A field can in principle change sign. A field that is declining now might continue declining, eventually becoming negligible, allowing gravity to potentially reverse the expansion far in the future, leading to a big crunch rather than eternal expansion. Or it might decline to zero and then rise again, oscillating, driving a cyclic universe. Or it might cross zero and become negative, leading to a collapse far more rapid and dramatic than the standard slow heat death, a scenario called the Big Rip, in which the expansion accelerates so dramatically that it eventually tears apart, first the cosmic web, then galaxies, then solar systems, then planets, then atoms, then the fundamental fabric of space-time itself. Each of these possibilities is consistent with some version of the mild hint in the current data. None of them is confirmed. The universe has not yet told us which path it is on, but the fact that we are close enough to hearing the answer, that current instruments are at the threshold of the precision required to discriminate between eternal cold expansion and something fundamentally different, is itself extraordinary. We are, in a real sense, at the moment when the fate of the universe is becoming an empirically decidable question rather than a purely theoretical one, and the voids will be central to deciding it, because whatever dark energy is, the voids are where it is most exposed, the voids are where it acts most freely, most completely, most without the complicating presence of matter to mask its effects. The voids are the windows through which the fundamental nature of space itself is most directly visible. If dark energy varies over time, the voids at different epochs will be slightly different sizes, slightly different profiles, slightly different internal structures than a constant dark energy model predicts. If dark energy varies over position in space, which some theoretical models allow, the voids will encode that variation in their geometry. If gravity behaves differently on cosmological scales than general relativity predicts, the growth rate of voids will deviate from the standard prediction in characteristic ways. The void is the most sensitive instrument in the universe for measuring the nature of space. And we did not build it. We found it. Nature provided it, built into the structure of the cosmos by the same quantum fluctuations that seeded everything else. Developed over 13.8 billion years by the same gravity and dark energy that shaped the galaxies and the clusters and the web. We simply learned to read it. This brings us to the seed planted at the very beginning of our journey. The image we introduced at the start, the detail we promised would not pay off until the end. We described the quantum fluctuations of the infant universe as whispers, tiny variations in the density of energy imprinted by quantum mechanics on the fabric of space during inflation and then amplified by the expansion to cosmic scales. We said these whispers became the seeds of everything. And they did. Every galaxy, every star, every planet, every living thing that has ever existed in this universe traces its origin to those quantum fluctuations. The matter that makes up your body was once part of a slightly overdense region in the primordial plasma, a region where the quantum whisper was slightly positive rather than slightly negative, where the density was 100,000th of a percent above average rather than 100,000th of a percent below. If that whisper had been the other way. If your patch of the early universe had been one of the slightly underdense fluctuations rather than one of the slightly overdense ones, that matter would have drifted outward over billions of years into the surrounding void, never gathering into stars, never forming planets, never producing the chemistry that leads to biology. The atoms that are you would be scattered through an emptiness so vast that their nearest neighbors would be light years away. You exist because the quantum fluctuation in your corner of the early universe happened to be slightly positive. That is not a metaphor. That is the literal, physical, observationally confirmed story of your deepest origin. The fluctuations in the cosmic microwave background, those 100,000th of a percent temperature variations we have mapped with such precision, are the baby picture of the universe. And buried within that baby picture, in the specific pattern of hot spots and cold spots, is the seed of every void and every galaxy and every observer that ever looked up at the night sky and wondered. The voids and the structures are not different things. They are the same thing. They are the quantum fluctuation of the early universe, expressed at cosmic scale over cosmic time. The overdense fluctuation became the galaxy. The underdense fluctuation became the void. The boundary between them is the wall of the cosmic web, the place where matter flowed from one side to the other over billions of years in response to the tiny difference that was there from the beginning. The void is the galaxy's shadow. The galaxy is the void's complement. They define each other. They cannot exist independently. They are the universe, reading itself. And here is what makes this not just beautiful, but important in a way that goes beyond aesthetics. The fact that we can read this story, that we can trace the chain of causation from quantum fluctuation to void to galaxy, to star, to planet, to living cell, to nervous system, to consciousness, to the act of looking up and asking why, means that the universe contains within itself the capacity to understand itself. Not perfectly, not completely. We are still 5% of the total picture, working with instruments that can see only a fraction of what exists, operating on timescales that are a rounding error in the history of the cosmos, but partially, genuinely, with accumulating accuracy and depth. The void is the context for this understanding. The void is the 330 million light-year sphere of nothing that surrounds the rare. Improbable, exquisitely structured islands where stars burn and planets form, and life organizes matter into the capacity for inquiry. The void is the silence that makes the signal legible. The void is the darkness against which the light of the galaxies, the light of the stars, the faint, pale blue light of a planet with oceans and an atmosphere and a thin, fragile layer of living things becomes visible. We are the light in the void, not metaphorically, literally. The photons streaming from every star in the Milky Way are traveling outward into the surrounding emptiness right now, crossing the wall of the local void, moving through the intergalactic medium, eventually reaching the walls of the larger structures beyond. Some of those photons will cross voids of tens of millions of light years before they encounter another galaxy. Some will travel for hundreds of millions of years through the great supervoids before their journey ends in the absorption by some distant detector, biological or technological, in some unimaginable future. The light of our sun left the solar system roughly 8 hours ago in every direction. Some of it reached the edge of the heliosphere. Some of it is heading toward Alpha Centauri, 4.2 light years away, where it will arrive in roughly 4 years from now. Some of it is heading outward into the local void, the tens of millions of light years of relative emptiness that borders our cosmic neighborhood, and it will not encounter another galaxy for millions of years. We are, in this specific and measurable sense, broadcasting our existence into the void, not deliberately, not with any message, just as the natural consequence of being a star-lit system embedded in the cosmic web, surrounded by the same emptiness that has surrounded every structure in the universe since the first voids formed from the primordial underdensities. The Voyager probes, both of them, humanity's most distant physical ambassadors, crossed the heliopause into interstellar space in 2012 and 2018 respectively. They are now moving through the thin plasma between the stars, part of the Milky Way galaxy, but no longer connected to the solar system's magnetic bubble. They carry golden records, physical disks encoded with sounds and images from Earth, with mathematical information, with the location of our solar system, with a greeting in 60 human languages. They were sent as messages to any intelligence that might someday find them, drifting through interstellar space for millions or billions of years. They will never cross the local void. They are moving at roughly 17 kilometers per second, which is extraordinarily fast by human standards and extraordinarily slow by cosmic ones. To cross even the nearest portion of the local void, they would need tens of millions of years at that speed. They will circle the Milky Way many times before they ever approach the void's wall. They are messages in a bottle thrown into a sea that is orders of magnitude larger than the bottle can traverse. And yet they were sent. Not because the senders calculated that they would be found, not because there was any reasonable expectation of success, but because the act of reaching out, of declaring our existence into the darkness, of treating the question of whether we are alone as one worth answering even at enormous improbability, is itself an expression of the thing that the voids have been teaching us all along. The universe does not care whether we are here. The void does not open to receive us or close to exclude us. The dark energy pushing the void walls outward operates with complete indifference to our presence or our questions. The baryon acoustic oscillation scale is not a message addressed to us. It is a physical consequence of physics, as impersonal as gravity, as indifferent as the speed of light. But we care. We look out into the void and we ask what it is, and we build the instruments to answer the question, and we train generations of scientists to analyze the data, and we commission the next generation of instruments before the current ones have finished speaking, and we write the papers and argue about the Hubble tension and debate the nature of dark energy, and map the positions of billions of galaxies with more precision than any previous generation of humans could have imagined. We do all of this not because the universe rewards us for doing it, but because the capacity to do it is itself one of the most remarkable things in the observable cosmos. The void is mostly what the universe is. We are the exception. The thin, improbable, exquisitely contingent exception that arose from quantum noise in a hot plasma 13.8 billion years ago, and has been, for the past several 100,000 years on one small planet, developing the capacity to understand the void that surrounds it. There is something that should stop you here, at the end of this journey, in the same way that standing at the edge of the Grand Canyon stops you. Not because the canyon is grand in any absolute sense, but because the scale of it, the sheer physical fact of it, makes something in the body recognize a magnitude that the mind cannot fully contain. The void is grander than the canyon. The void is grander than the Milky Way. The void is grander than the observable universe in the sense that the void, the true void, the state toward which the entire cosmos is moving on timescales longer than the current age of the universe by factors of trillions, is the final context in which all of this, the galaxies and the stars and the planets and the living things and the questions and the instruments and the understanding, will eventually be embedded. We are not moving away from the void. We are moving toward it. Everything is. The stars are burning down. The gas reservoirs that feed new star formation are being depleted. The structures of the cosmic web are becoming more isolated as the expansion separates them beyond causal contact. The universe is, on its deepest timescales, becoming more void than it already is, and it is already, by volume, overwhelmingly void. This is not cause for despair. It is cause for the precise opposite. If the universe is moving toward the void, and if we exist now, in this narrow window of cosmic time, when the structures are still here, and the light is still burning, and the signals are still readable, then what we do with this window matters in a way that is not diminished by the eventual cold. The meaning is not contingent on permanence. The understanding is not less real because it is temporary. The question is not less worth asking because the questioner will not persist forever. The void will win in the end. It always wins. It is winning right now, slowly, at the rate of the accelerating expansion, pushing the walls of every supervoid outward by a few more kilometers per second per year, draining a few more grams of matter from the underdense regions into the surrounding filaments, stretching the fabric of space by increments so small they are detectable only by the most precise instruments humanity has ever built. But right now, in this moment, the light is still here. The galaxies are still visible. The cosmic microwave background still carries the fingerprints of the first 380,000 years. The baryon acoustic signal is still readable in the distribution of the galaxies. The voids are still measurable, still growing, still informative, still teaching us about the nature of space and time and the force that will eventually consume all structure. And we are still looking, still asking, still building the instruments and training the minds and expanding the picture, still finding in the emptiest places in the universe the fullest answers to the deepest questions. The void is not the enemy of meaning. The void is the condition that makes meaning visible. It is the dark that makes the light legible. It is the silence that gives the signal its shape. It is the 330 million light years of nothing that surrounds the something, and in surrounding it, defines it, and in defining it, makes it possible for the something to know what it is. Look up tonight, if you can, not at the stars, though the stars are worth looking at. Look at the spaces between them. The dark between the stars is not empty. It is full of structure, threaded with the cosmic web, traced by filaments of dark matter, crossed by the ancient photons of the cosmic microwave background streaming in from every direction. But beyond the structure, beyond the web, beyond the walls and filaments and clusters, in the great spherical hollows that occupy 80% of the volume of the observable universe, there is the void. It is expanding right now. It has been expanding since before the Earth existed. It will be expanding long after the last star burns out and the last black hole evaporates and the last quantum of structure dissolves into the final, featureless equilibrium. The void will be there at the end as it was in a different form at the beginning, as it is now surrounding the rare and improbable islands of matter and light and life. We looked into it, we measured it, we understood at least partially what it is and why it is there and what it means for the future of the cosmos. We found in the emptiest place in the universe a message written in the geometry of space itself, encoded in the frozen echo of primordial sound, signed by quantum fluctuations from the first moments of time. The message is not addressed to us, but we were the ones who read it, and that is everything.